So the topic of my talk today is perspectives in math and art. So there are these two paintings over here. The painting on the left is an example of prehistoric cave art, and the painting on the right is an example of Renaissance, European Renaissance painting. So what is the central difference you notice between these two paintings? Can someone? Yes, sir. Amount of objects. Okay, that is the themes are different. That is clearly true. But what is the central?
Sorry. You can perceive the depth in the second one.
That's correct. Exactly. So both paintings are appealing in entirely different ways. We are not discussing the aesthetics. One obvious contrast is that the painting on the right gives a feeling of depth which is absent in the one on the left, which someone remarked on that. So we will dwell into the mathematics behind the feeling of depth that paintings like the one on the right create. So Renaissance art, the Renaissance time actually gave rise to a rich interplay between art and math. And projective geometry was the branch of mathematics that was born out of that. So if you go back to that, if we just go back to that painting, so I'll just remark on that notice that the parallel lines on the floor, when extended, meet at a point, which is called the vanishing point in the painting on the right. Let's go back again and see that. So you can see that these lines, tiled floor lines, they meet at a point. So in high school Euclidean geometry, we have learned that parallel lines do not meet. In contrast, in projective geometry, which is the geometry associated with the Renaissance art, parallel lines do meet at a finite point. That's the central difference between Euclidean geometry and projective geometry. So this is something that is very familiar to all of us. We have all seen railway lines, railway tracks meeting at a point. And these are parallel lines which meet at a point. So this is an example of classic painting, which is called the School of Athens from the Renaissance time. And Renaissance artists would often locate the focus of the theme of the painting at the vanishing point. So for instance, in the School of Athens, you see Plato and Aristotle's figure somewhere in the middle is the vanishing point. And this figure is modeled after Leonardo da Vinci. And this is a very interesting painting. It's full of examples of like stalwarts belonging to various art forms and mathematics and sciences. The painter Raphael is also somewhere over here. And it captures the mood of the Renaissance time, where there was a sort of blurring of the distinction between the sciences and the arts. So projective geometry, just to give a brief history, 300 AD, Pappus's theorem was the earliest theorem in projective geometry. And in 1600 AD, Pascal's theorem was formulated, and it was basically the generalization of Pappus's theorem from straight lines to conics. And in the 1600s, there's a significant theorem due to Desargues, who was a typical Renaissance person, an engineer mathematician interested in art. So around the time of Desargues' work in the domain of projective geometry, Descartes and others introduced Cartesian geometry. And because of that, somehow the emphasis shifted towards Cartesian geometry. So the world saw a dominance of Cartesian geometry and calculus and a decline in the interest in projective geometry. However, there was a re-emergence of projective geometry in the 1800s thanks to the works of Mobius, Klein, Chasselet, and others. So let's discuss the basic notions in projective geometry. Meets and joins. So the intersection of two lines is called a meet, and the line joining 2 points is a join. So Pappus's theorem can be stated like this. Given 3 points that are collinear, 3 points A, B, C, which are collinear, and 3 other points, A prime, B prime, C prime, which are collinear. Now you consider joining A prime, B, A, B prime, then B, C prime, C, B prime, and C, A prime, and A, C prime, crosswise. Then you end up with 3 intersection points indicated in red. The claim is these 3 points, red points, are collinear. That is Pappus's theorem. Then the generalization to conics came from Pascal. Pascal's theorem is an extension of Pappus's theorem to conics. So you can see that, okay, this is a particular conic section that is taken like an ellipse, and there are these 6 points on the ellipse. And then here also, if you join these points in a similar manner to what was done for Pappus's theorem, crosswise, you end up with 3 intersection points indicated in white, and the claim is these 3 points are collinear. So projective geometry is really the geometry of the straight edge. So for instance, even conics can also be generated by the use of only a straight edge. I've written ruler, but it's actually something much simpler than a ruler also. If you have a ruler and you get rid of all the markings, that's what a straight edge is. So in projective geometry, you can generate even curves out of straight lines. So this is a video that I would like to show.
Start with a line with, say, 3 dots on it. And then we're going to add an extra yellow point. This is what's called a center of perspectivity. And we're going to do a perspective from this blue line onto this green line. So what that basically means is that we're going to draw a line through every point of our blue line that we're interested in and see where they end up. So it's as if one had put an eye at the yellow points and then observe where the corresponding points would appear on the green line. And so essentially, by this perspective, we get these new 3 points on the green line. So that's what's called a perspective, or maybe a perspectivity with respect to the center of perspective, which is the yellow point. And now we're going to do another perspectivity. So we're going to do one with respect to this orange center of perspectivity here onto this red line. So if you try and ignore the blue line and the blue and yellow lines, you should be able to see again what's going on is basically analogous. We're just putting this orange point down, drawing lines through the green points, and seeing where they end up getting sort of moved to onto this red line. And so it's just another perspectivity. And so basically what we've done is we started off with 3 blue points, and then we did one perspective on them to change them onto the green line. Then we did another perspective on them to change them onto a red line. So we've done a sequence of perspectivities. That's called a projection. So we've done a projection from the blue line onto the red line. Anyway, what's the method? Well, basically, we just see this big red dot here. Hopefully you can, if you pause the video or something, you can convince yourself this is the projection of this original big blue point. Now all we do is link the original object to the red point it's been projected to. And then I'm doing this in GeoGebra, which has this wonderful feature called trace, which basically means that if an object moves around, you can see as if one was viewing it with a long exposure camera. And so now, if I just drag around this blue point here, one can see that it's actually sweeping out a curve. In fact, it's sweeping out an ellipse, which is very interesting. So all the different conic sections can be generated in this way. It just depends on the original setup of the objects.
So here's an explicit demonstration of
I'm going to
how
play
you
around
can
with this a
generate
bit
an
and
ellipse
alter the
using just a straight edge by taking various perspectives. That's how it was done. Likewise, you can generate all other conics. And conics are, as you know, are generated by taking sections of a cone using a plane, like circle, ellipse, parabola, hyperbola, all are conic sections. As I said earlier, the Renaissance artists realized that parallel lines meet at the horizon, and straight lines must be represented by straight lines. And the image of a conic is also a conic. For instance, the image of a circle is an ellipse. This will get clearer as we go along. So, in fact, projective geometry captures something essential about conics. It sort of reminds us of the common origin of all these conics. It sets an equivalence between a parabola, a hyperbola, an ellipse, and a circle, reminding us that all of them have been generated from the cone. So they have a common origin, and they actually are equivalent from the perspective of projective geometry. So we'll see how. So for instance, consider a parabola on the Cartesian plane, this thing on the right. So you have a Cartesian grid, mutually perpendicular, and you have a parabola, y equals x squared. So what happens to the parabola if we go to the artist's canvas or the projective plane? So here, clearly, because of the railway track effect, there's a convergence of these parallel lines parallel to the y-axis. And now if you take points on the parabola in the Euclidean plane, you find that one by one, as you plot the points, they trace out an ellipse. So a parabola in the Cartesian plane translates to an ellipse in the projective plane. So this is the point that I had made earlier also. So thus in projective geometry, all conics, circles, ellipses, parabolas, and hyperbolas are equivalent. So both Desargues and the artists realized that points at infinity need to be added to represent the horizon. And this is needed both for art and math. For example, math theorems like Desargues' theorem and Pappus's theorem. One hallmark of projective geometry is the absence of reference to any measurement, unlike Euclidean geometry. For instance, all lines are extended in projective geometry. We don't think in terms of line segments, but extended lines. In fact, if you remember the statements of the Pappus's theorem or the Pascal's theorem, I didn't make any reference to any length of a line segment or even the angular measures. I didn't. Those things were not there in the statement. So that's a hallmark of projective geometry. So projective plane is the ordinary plane plus a line at infinity. In a projective plane, any two lines meet at a point. This is a very interesting fact, actually. If you think about Euclidean geometry, there's a big difference between parallel lines and non-parallel lines. So projective geometry unifies all these lines and says that all lines, given any two lines, they meet at a point. And in a projective plane, any two points join to make a line. So you see the symmetry between lines and points in these statements. So thus there is a duality between points and lines. So Poncelet was born at the time of the French Revolution, and he brought about a revolution in math. He was a product of the French Revolution. He was a child of the French Revolution, and he also brought about a revolution in the realm of mathematics. So projective geometry, this is due to Poncelet. There are two key principles due to Poncelet. One is the principle of continuity. So this is a diagram that I've taken from Ramanujan's article in Resonance. So as I was saying, there is no difference between parallel lines and non-parallel lines. This is brought out from this figure very clearly. If you have two parallel lines, one of them, this is one fixed line and that is another, and you have a bunch of lines which actually meet at a point, and these lines, the ones which are meeting, imagine tilting them. Then in the process of tilting, you make them parallel to the fixed line. So you see a continuity between parallel lines and non-parallel lines. This is a feature of projective geometry. And this feature was noticed by Poncelet. And the other one is the principle of duality, which I had alluded to earlier also, interchanging the roles of points and lines. If a theorem holds in the projective plane, its dual holds in the dual projective plane. Thus, there are duals of all theorems, Pappus's theorem or Pascal's theorem, and so on. There dual versions are also present, where you interchange the roles of points and lines. The dual theorems hold true, just like the theorems themselves. So complex projective geometry, let's come to that. So you know that if you take the intersection of a conic and a line, that would give rise to a quadratic equation. For instance, if you take a simple example of a parabola, y equals x squared, and a line, y equals x. Clearly, if you take the intersection of these two, you end up with a quadratic equation. So here, when we take this picture, we have considered an ellipse and a line. So if you look at the line AB, that intersects the conic at two distinct points, corresponding to the two distinct roots. EF, on the other hand, is a line tangent to the conic. So it's tangent at one point. Actually, another way of saying it is it intersects the conic at two coincident points, like coincident roots. Now, the problem comes when you look at CD. CD doesn't seem to intersect the conic at all. So what is happening? So this is sort of disconcerting, right? So that as if there is some kind of breakdown of continuity. So how do you understand this? So CD actually intersects the conic at 2 points in the complex plane. Instead of the real plane, if you go to the complex plane, you see that there are two intersection points in the complex plane. So introduction of complex coordinates enables restoration of continuity. So there are several applications of projective spaces in physics. So before going to this statement, I'll just start with the example itself, the simpler example. If you consider in the realm of real numbers, for the real projective line, what is it? I mean, whether if you're an artist or a mathematician, you'll think the same way. So you have a line, and you're adding a point at infinity. So you get a structure like this on the one on the right, right? So that is an example of RP1, real projective line. Now, when you go to the domain of complex numbers, you have two real numbers, right? So you can see that the generalization of that would give you a sphere. This is called the Riemann sphere. So now, and it is called CP1. It's a complex projective line. So complex projective spaces like CP1 come into play in the realms of quantum information. This is the space of qubits, and geometric phases, which have several applications in physics, geometry, quantum computation, and so on. I won't go into these in detail now. Okay, so now let's come back to art. So projective geometry through drawing. So this is a perspective machine illustration, Dürer's Dürer was a great artist, and many of these artists had also built interesting machines to make accurate perspective drawings. So this is Dürer's perspective machine. So what are the elements which go into drawing? So you have the object, a picture plane, and the eye, right? So consider drawing an apple on a table. So the canvas is placed between the object and the eye, and the drawing is constructed by connecting the intersection points of the sight lines and the canvas. This statement will be clearer when I go to the next slide. So here, instead of an apple, I consider a flower in a pot. So here is the 3D object. This is the eye of the artist, and this is the canvas. And you see that these are the sight lines, and you get a perfect representation of the original object on the picture plane. So in the 15th century, Italian architect Brunelleschi demonstrated the idea of perspective using a mirror with a hole in it. I won't dwell into it. So this is also an example of a machine that was built by an architect to make accurate structures. You can look up this YouTube link to see it in more detail. So this is Leonardo da Vinci's perspectograph, which is also, you can look up this YouTube to know more about it. It's also an interesting structure. And we have mainly talked about one-point perspectives. So there are also these two-point perspectives. This is an example of a two-point perspective to draw an architectural structure. And apparently the first known example of a two-point perspective was by somebody in 1505. And as we had seen already with the first painting that I'd shown from the Renaissance, there were these tiled floors. So imagine considering the lines of the edges of the tiles. So that family of lines will meet at a point. Then you consider all the diagonals, they also meet at another point. And the other set of edges also meet at yet another point. So all these 3 points lie on a line, which is the horizon. So this is a very interesting object. It's called the camera obscura. It's in fact something that you have studied in physics in high school, the pinhole camera. So, and you may have even built it with a shoebox and some tracing paper and so on. And so here you see an artist sitting inside a camera obscura and painting the landscape which is outside. So all he does is puts the canvas on this wall, and because the pinhole camera image is upside down, he produces an upside down image of what's there out there. And all he needs to do is to just take the canvas and turn it around and get it right side up. And interestingly, elements of perspective were present in medieval European art as well. There are examples way back in 1389. So there you see that objects which are very far away appear to be smaller. And even more interestingly, in Pompeii, between 59 and 79 AD, there are examples which are seen on the murals on the walls. So there are mural examples where you see the use of perspective. And this I had seen with my own eyes, because when I had gone to Pompeii, I was really struck by some examples of three-dimensional looking paintings way back then. So one wonders why, how come, like so early on? So one way of thinking about it is that artists also have an intuitive way of visualizing the world and seeing it accurately, in its entire three-dimensionality. And they would try to represent it as faithfully as possible. So that's what was done. It's not that they understood the mathematics in that at that time. So although there were examples of perspective in art prior to the European Renaissance, The merging of mathematics and art happened only during the Renaissance. So an intuitive understanding of perspective was perhaps there amongst early artists. However, a comprehensive understanding emerging from the interplay of art and math did not happen before the Renaissance. So there is this interesting theorem by Desargues' theorem. So the statement is, if two triangles are in perspective via a point, they are in perspective via a line. That's the statement of Desargues' theorem. So if you take ABC and A prime, B prime, C prime, these two triangles are, if they are in perspective via a point, say O, the claim is they're in perspective via a line L. And actually what you need to prove here really is that given that these two triangles are in perspective with respect to O, you need to show that the intersection points of the corresponding sides, there are 3 intersection points, they all lie in a single line, on a single line. So this is almost like the proof is so obvious, so that's why I'll go over it. So all that you do is you notice that ABC lies on a plane. The triangle ABC lies on a plane, and the triangle A prime, B prime, C prime lies on another plane, right? There are these 2 planes. And these 2 planes obviously intersect at a line, L. So now, if you consider corresponding edges of the triangles, the intersection points of these edges obviously will also lie on this same line. Right? So that is really the proof. And one more point is that duality really helps you understand certain things. For instance, perspective via a point is easy to understand, both from the point of view of art and mathematics. No? That's when we've discussed the eye of the artist lies here. But what is perspectivity with respect to a line? To understand that, I at least found it very easy to think in terms of the dual plane. In the dual projective plane, the line is a point. So again, in the dual projective space, you have a perspectivity with respect to a point. So just to conclude, European Renaissance saw the merging of art and mathematics. Projective geometry was born out of that intersection. Projective geometry offers a path for artists to appreciate mathematics and for mathematicians to appreciate art. Projective geometry is indeed the most fundamental and the underpinning of all other forms of geometry. It has several applications in physics, quantum information and quantum computation, to name a couple. And then I'll just end with Leonardo da Vinci's quote, "Art is the queen of all sciences." So there are a few references. This is Ramanujan's article in Resonance, which was appeared in 1997. And Weilberger has an excellent set of lectures on YouTube. And this is, some of my talk was based on his lectures, but there's a whole series of these lectures. Many of them go to quite high level. So if you are really interested in this subject, I encourage you to look up. And I had also consulted a brief history of perspective in European art. There's a YouTube link. Thanks. I think I finished early. Yeah. Yeah.
In the ellipse diagram, when we were seeing different lines, one was intersecting at 2 points, the another one was intersecting at a, you said there were 2 coinciding points, the tangent.
Points. Yeah,
How
yeah.
did we know that there were 2 points which were coinciding?
That's the way you think about tangents, right? So if you have an ellipse and you consider a line, and you keep moving the line, at some point it gets to be tangential. So basically these 2 points keep approaching each other until they coincide. That's in fact the definition of tangency. So that's what it is.
And also, I didn't get the third line, which you said it met at 2 points. The ellipse and intersected the ellipse at 2 points in a complex plane.
Yeah. So basically, that diagram was done in the real plane, right? So there we saw that. Suppose this is the ellipse. Anyway. And then you saw that it looked like it was not meeting at all. So that's the fact that it's not meeting is only a consequence of the fact that we are restricting to reals. If we go to the complex plane and use complex coordinates, we'll see in the complex plane there are intersection points. That's the point I'm making. So it's like if you take the quadratic equation, you can in general have real roots, 2 real roots. And if you have a quadratic equation with real coefficients, you can have 2 real roots, or you can have 2 complex conjugate roots, for instance. So it's like that. Yeah.
Like that any two points, any two lines meet at a point, and that 2 points join to meet a line in the projective plane. But ma'am, doesn't this apply to Euclidean geometry as well?
Yeah,
Because we
how?
take 2 points and we join a line between them.
That's correct.
At the same time, 2 intersecting lines intersect at a point, right?
That's the point. You take 2 lines which are tilted like this. They do intersect at a point, but would you say that these 2 lines intersect at a point?
Okay, so this
Euclid
applies
geometry?
to all lines.
That's right. That's the
Okay.
thing about projective geometry.
Okay.
And that's what that intuition comes from the Renaissance art very beautifully. Like that painting, those set of lines on the mosaic floor, on the tile floor, the meeting at, or the railway track. This is a railway track effect.
And ma'am, I had another question. So since like perspective has kind of like merged into maths quite some time ago, so even today when we draw diagrams in physics, like if we look at it in sense of perspective, most of them are inaccurate, right? When we draw a cube or a cuboid, we draw a square like this, we draw another square behind it, and then we join all the 4 sides to create the third, like, yeah, to make it in 3 dimension. But if we look at it in point of perspective, that would be like the 3D form of a parallelogram. It wouldn't be a cube or a cuboid.
Actually, the main point about perspective is you fix a point of view and stick to that. So from that point, how does the world look like? And you have to be faithful to that. So you can draw individual 3-dimensional objects here and there, but everything put together should make sense. So that's what the beauty of
So, but why don't we use the ideas of perspective when we draw like our technical diagrams?
Yeah, I think now now I'm sure people do use these because it happened. The revolution happened long back.
Yeah,
So
because even in textbooks, like when I was also in 12th, most of them were like,
I think in some sense the art has degenerated, you can say, but I mean art. I wouldn't say that because art has changed. Art is a growing tree; it keeps changing. Picasso has some appeal which is different from Renaissance art. Programs, yeah, perfect. You can do very with the computer programs you can do absolutely perfect. Perspective better than anything else. Yeah.
And also some artists don't want perspective. I'm not talking about the technical point.
Yeah. Like people like Matisse and people like that. They were perfectly capable of drawing like classical art, Renaissance art type of paintings, but they chose to break those rules. So the artistic freedom. Yeah.
The first theorem that you have shown,
Papo's
yeah,
theorem, yeah.
that thing. Could you please show the slide again?
Yeah, yeah. Yeah. You wanted to say something? Yeah. Oh, I think she wanted. Okay.
Are equivalent in projective.
Okay, okay. We'll go back to that. I had given a specific example. This is a parabola. This is an Cartesian, usual Cartesian plane, right? You take a mutually perpendicular Cartesian grid and you have drawn a parabola. So now you're asking what will happen to this parabola when we go to the projective plane. So as I said, these lines which are parallel to the y-axis, because of the railway track effect, they'll meet at a point on the horizon, right? So now you can do this exercise. I urge you to actually try it on a graph sheet. And so take all these, each of these points and see what those points look like on this plane. And you'll see that you'll end up with an ellipse. So a parabola has become an ellipse. So that's the sense which there is an equivalence.
Like the lines from this side, they are
Yeah.
merging and the
Right,
point
right.
goes
That's
higher.
how it's the effect is happening. And you can try it out with other conics also.
Okay.
Ma'am, as I was asking, in Papo's theorem, there is two intersecting line and each line has collinear, three collinear points, right? So after that, like how is that middle line coming?
Okay, I'll go back there. Yeah.
That red
So,
middle line.
yeah. So what is happening is that you have one line here, A, B, C are there, another line, A prime, B prime, C prime, right? So you joined A and B prime by this yellow line, right?
Yeah.
And B and A prime by this yellow line. And you get an intersection point, red intersection point, right? And now you take the two green lines, they are also intersecting at another red point. Then you take the two white lines, they intersect at the third red line. So the claim is that these three red points meet, are collinear.
So basically the theorem suggests like those 3 points will be collinear.
Collinear, yeah, that's the claim.
Ma'am,
I
how
haven't
is
proved
it
it. But
associated with Pascal's? How is this theorem associating to Pascal's theorem? Like you mentioned.
Okay, I'll show you. So Pascal's theorem is, what is it? Pascal's theorem looks like this. I am giving the particular context of an ellipse. So just for the moment, just imagine opening this out. Then it will be like two parallel lines of that. Yeah. So these 3 points are on one arc, and these 3 points are on the other arc, and you're joining them crosswise. And the claim is that these 3 white points are collinear. So that way, it's a generalization from straight lines to conics.
Thank you, ma'am.
Yeah. No, I don't think there is any statement, nothing like that, isn't it?
Can you show the principle of continuity again? And
Yeah.
what do you mean by the tilting of the lines? What you
Okay, I'll
explained?
show. Yeah. So you have these two lines which are clearly parallel, right? One fixed line and this one, right? But if you take this family of lines, this 1, 2, 3, 4, 5, 6, they are intersecting at a point, right? So there seems to be an intrinsic difference between these 6 lines and these 2 lines. These 2 lines are parallel and these lines are intersecting. But the claim is that in projective geometry, there is no real difference between this bundle of lines and these 2 lines, in the following sense that now if you imagine tilting these lines, the ones which are intersecting at a point, you can slowly turn them and make them parallel. I'll show you like this. Suppose they are like this set of things which are intersecting. Intersecting. Imagine taking this and tilting it. It's like a, right? Then it will become parallel to this. You can do the same thing with all these lines. So that's the principle of continuity. Yeah.
Pascal's theorem. To go from Pascal's theorem to Papu's theorem, you have to think of two lines as being also a part of a conic.
That's correct.
You take a cone and slice it vertically.
Yeah,
then you
exactly.
Get to it. Okay.
That's right. So basically, in fact, it's a larger set than what I was saying. It's not just the equivalence of conics, it also sets an equivalence between conics and straight lines. So from those lines, those curved lines, you can go to straight lines, because you can think of the straight lines as also being formed from conic, from taking sections of a cone. Yeah. Okay, I'll tell you, there is a connection with special relativity for sure. I'll tell you briefly what it is. In Galilean relativity, there is no upper limit on the speed, right? The speed can be infinity. In contrast, in special relativity, there is a speed limit set by the speed of light. And this is exactly analogous to the statement that in Euclidean geometry, you have parallel lines which don't meet, or they meet at infinity. And whereas in the projective geometry, the parallel lines meet at a point. So projective geometry is analogous to special relativity, and Euclidean geometry is analogous to Galilean relativity. So special relativity, certainly there is a connection. Principle of duality.
Ma'am, can you just explain what is dual projective plane? I didn't get it.
Okay, dual, okay. Basically, the statements about what we had seen, let's go back a little bit. Yeah, this one. So, as we discussed earlier, in a projective plane, any two lines meet at a point, right? And in a projective plane, any 2 points join to make a line. So it looks like you can, if you take the first sentence and interchange line and points, you get the second sentence. So lines and points have an interchangeable role. So that's the sense in which they are duals of each other. So, yeah. This is a very interesting question that you asked about connection to relativity. There's a nice article on the net. General relativity. That part I'm not sure about. Maybe you can comment on the connection with general relativity. Connection between. Yeah, that's true. Yeah. So I'm just restricting to special relativity. So there is indeed a connection between projective geometry and special relativity. That's what I mentioned. There's a nice article called Projective Geometry and Special Relativity. If you just type it in on the internet, you'll find the article. I've forgotten the name of the author, but there are these drawings also, which shows this set of parallel lines, and then if you go to special relativity, they become a finite point, and because of this finiteness of the speed of light. They are bringing in something extra, which you have to understand while reading them. Yeah. Right, right,
So
right.
similar to that, like if we talk about the geometric, the general relativity, the geodesic domes and all we talk about, so maybe it can have some connection with the general relativity part
Yeah,
of that.
I think those manifolds, those kind of manifolds would come up. Right? What she's saying is just like in the space of qubits, the block sphere is represented by CP1. Likewise, because general relativity involves curved manifolds, there could be some connection with projective spaces. No, that's the, yeah, the special relativity one I had mentioned. Yeah, that's correct.
Shouldn't we be saying that they seem to meet at a point? Because this is all about perspective. So I understand that mathematically we might need to represent the point, but isn't it too definitive to say that they meet at a point
Yeah,
rather
I
than
would
saying
say
they
it is very
seem to?
definitive. You know why I would say it's very definitive? The example comes from the art. When the artist has to represent the floor lines on the floor, the artist, she finds that she has to put a certain dot. And that's a definite finite point on the canvas. So it is indeed a definite point.
Yeah, but then again, art is just an image of what we can see, because like that's just I don't know, the amount of how much our eyes can see into the distance, right?
No, but
Is that not
the
a
artist is
projection
putting
of?
a very definite point on the canvas.
Yeah, the artist is putting a definite
that
point,
is,
which doesn't really
so that is a
exist.
very real thing.
Yeah, so inherently, isn't this a little bit?
I think what is more apparent, what I would say that I would call apparent in your language is when we see the railway tracks, you see that it seems to be meeting.
Yeah,
somewhere.
but
so
if
that
you
then there is some ambiguity. Okay, maybe
if you
maybe
pop
or
on
maybe
a
not.
train and then you drive, there is no point in
Yeah.
it because it's just a parallel railway track till the end.
Right. So artists or mathematicians are doing exactly the same thing. They're putting a finite point on the canvas, and mathematicians are saying that apart from these other points, we are adding the point at infinity and creating this projective space.
Beautiful.
So it's a very interesting interplay between apparently very apparently distinct domains of endeavor. When people say, "Oh, art has no connection to math," or "science is so different from," it's not true. Yeah.
I have an addition to that point. Maybe we can say that it's just if when we scale it down to the size of a paper, we need that one point. But in real life, the distances are so large that we can like assume that that point is too far and we can't just. But on a paper, we are just scaling it down and we need that one definitive
On a
point.
paper, actually what we are doing is this, I'll show you. Yeah, this is what we are doing. See, this kind of stuff. The sight lines are being connected to reconstruct things. And so we are putting, this is a simple example, but in the context of those lines on the floor, we are putting a definite point on the canvas. So there's no ambiguity there. No, I would say that this is the projective plane. Canvas is the same as a projective plane. There's no difference.
So, so like when you're saying that like when we see it from afar, we just see a point, right? And then on the paper also we're marking the point as a definite point. But this is what we observe while we're standing at a specific point, right? Like it's not
Yeah, it is a
necessary.
perspective.
It
That's
is a
why we call it a
perspective.
perspective.
We're just standing there. So until until and unless we actually go to that position and figure out, oh yeah, these
No.
two lines are
No,
different.
if we go to that position, they won't look like they're
Yeah,
merging.
but then again, our situation has changed, right?
Yeah, I think that's the reason why it's called perspective.
Exactly. So we can't say that, but like, this is what I believe, that it's not definitive ki just because we are putting a point, it's not there, sort of a thing. Because from where I am standing, I see a point.
Yeah, that's right. That's the thing. You have to fix that. You cannot keep saying that. Oh, that's what, you know. If you look at some of this miniature painting, it's a juxtaposition of perspectives. So it's saying, okay, I'm taking this point of view, then I'm taking this point of view, and I'm putting all of them together. Here they are not doing that. They want to capture realism. So take one point of view.
To that point, when we talk about spheres, like when we talk about Earth, we have longitude and latitudes which look like real, parallel lines. But when we actually see and when we try to see them and when we look on a sphere, that those parallel lines might not be parallel. They might seem to converge at a point. They might converge at a point and intersect at a point.
That's because we are dealing with a compact manifold. Yeah.
Yes, ma'am. And that's that's the thing that perspective actually, matlab, like that's we can say from the non-Euclidean geometry, things are different from Euclidean geometry, like where that the lines are parallel, and in non-Euclidean geometry that those parallel lines can intersect to each
That's
other.
true. In fact, Euclid's fifth postulate was the thing that had to be changed to accommodate curved geometry.